Hi guys, today we're going to learn about optimization. Let's look at this example. A particle moves along the x-axis so that its position is given by the function s of t is equal to t to the power of 3 minus 5t squared plus 12t for t that is between 0 and 4. We want to find the minimum velocity of the particle at the time at which it occurs. Justify your answer. For this problem, there's going to be two methods that we're going to see. The first method that we're going to use is the candidate's test, or what you also know as the extreme value theorem. So the first situation that you need to see here is that we want the minimum of velocity. So the minimum of velocity tells you that first we need to find the equation of velocity, and after that we're going to find the derivative of velocity and set that derivative of velocity equal to 0 to find the critical numbers. After that we're going to make the table as we were doing with the extreme value theorem, showing the t values at the endpoints and the critical numbers along with the v of t values, like we did when we found the absolute maximum and minimum back in the day. Okay, so now that we know what we're going to do here, you know that v of t is going to be the derivative of the position function. You know that that one is going to be 3t squared plus, well, not plus actually, it's going to be minus, let's do it here, it's going to be minus 10t, okay, plus 12. Okay, so we have that is going to be your velocity equation. So we want to minimize this equation. Therefore, we need to find the derivative. The derivative of this one is 6t minus 10. Okay, so we have the derivative here. So what we want to do here is we want to equalize it to 0 because we want the critical numbers. When you solve that, you have that t is equal to 10 over 6, which you know that we can simplify as 5 over 3. So this is a critical number, okay? Therefore, we have only one critical number, which is inside the interval 0, 4. Okay, so when I do my table for the candidate's test or the extreme value theorem, what are you going to do? Well, you have here, you create your table. You know that in your table, you are going to have the extremes. In this situation, we have t, and we're going to evaluate this in your equation v of t. Okay, the extremes that we have are 0 and 4. Okay, and the critical number that we have in this situation is 5 over 3. Okay, so when we plug the 0 here, it's easy to see that you have that's 12. When we plug the 4 here, you know that that's going to be 20. And when we plug the 5 over 3 over here, this cancels. So this is going to be 11 over 3. Okay, that you know that this one is roughly 3.667. Okay, so that's what we have. Now, typical EVT problem, we compare the numbers and we know that in this situation we wanted the minimum, therefore you want the smallest number here. The smallest number here, you know that it's a 3.667, so that's going to be your minimum, okay? And that's pretty much it. We're going to conclude. So what we know is that by extreme value theorem, or by candidate's test, whatever you prefer, the minimum, okay, velocity is 3.667, okay, and it occurs, okay, at t equals 5 over 3, okay, and that's pretty much what we have for this problem. Okay, so remember, this is the first method that we have. Now, what is the second method? The second method that we have is pretty similar, and it's an old friend of yours. This is going to be the first derivative test. Okay, so since you have that it's the first derivative test, we are going to pretty much do similar things as the previous problem, well, the previous method. You are going to find your equation of velocity. After that, you are going to find the derivative. You are going to set your derivative equal to 0, find the critical values that should be the same. Then you are going to do your sign chart and find the value of t, where v of t is a minimum that way. Okay, so pretty much we have the v of t that you know that it's going to be exactly the same as we had it before. Okay, it should be the same. Then you have the b prime of t, that it should be exactly the same, the 6t minus 10. Then you're going to equalize it to 0, same thing. Okay, and then you have that your critical number is 5/3, and you have that that's your critical number. Okay? In this situation, we're not going to do the table for the extreme value theorem. We're going to do a sign chart, or an interval situation. So you know that I start at 0, then at 5/3 I have a critical number, then 5/3, and then you go to 4. Okay, so then you're going to evaluate your b prime. Remember, we're evaluating this guy. So you plug a number in between 0 and 5/3. Okay, when you plug, let's say 1, that one gives you negative, and then you plug a number between 5/3 and 4, let's say 3, and that one should give you positive. Therefore, you can see that the derivative is changing from negative to positive here. Therefore, that's a relative mean by first derivative test. Okay, so now let's conclude. So we have that the minimum velocity, okay, is, we don't know, but you can plug the 5/3 that we already know from the previous one, the previous problem, that it was 11/3, or it was 3.667. Okay, so it's either 11/3, well, let's be original, 11/3. Okay, and it occurs, okay, at t equals 5/3, okay, because, and we know that this is happening because b prime, okay, changes from negative to positive there. Okay, so here you are justifying why it's a minimum. Okay, so you can see here my justification of why this 5/3, it gives you the relative minimum. Please note something that is super important. Okay, if the absolute max or mean happens at the endpoint and not in a critical number, you must use the candidate's test or EBT. Okay, so I highly recommend you, if possible, use candidate's test. Okay, my first shot is always the candidate's test in this situation, but you can also solve it via the first derivative test in case that you don't have the closed interval. Okay. For this example, what we have is a man is standing on the edge of a river and wants to travel from his location to his camp in the minimum amount of time. His camp is 5 miles to the south and across the river, which is 1 mile wide. If he can travel on foot at 6 miles per hour and he can swim at 3 miles per hour, how far should he walk towards camp before swimming across? Please note something. Assume that once he enters the river, he will swim directly straight line to his camp. Okay, so he's going to pretty much do a straight line, okay, to his camp from when he gets into the river. So let's draw the situation so we can understand what we have here. So my guy is over here, this is my guy, and he's next to the river, right? So this is the river. The camp is over here. Okay, so we have a camp, here's the fire, everything, right? Okay, so what do you know? We know that this is the river, okay? So you know that the river, from the width of the river, you know that it's 1 mile, okay? Second thing that you know, according to this, his camp is 5 miles to the south, okay? So what we know is that the guy from here to here, okay, let's put it from here to here, this is 5 miles, okay? So that's what we have so far, okay? So what are we going to do? Well, it says here that once he enters to the river, he will swim directly and he will come here, okay? He will arrive to this spot, okay? So what we can see, let me get the ruler so you understand the situation, is either the guy does this, here, somewhere there, right? So you see it? So that's what's going on. So I'm just going to, for the practicality of the situation, I'm just going to draw it there, somewhere in between, so we can do a good rough sketch. Okay? So what are they asking? They are telling you, how far should he walk towards the camp? So pretty much they are asking you about this section. Okay? So that section, because that's the section that he's walking. Okay? And that one is not set. So I'm going to call that variable, well, that section y. Okay, since it's a vertical line, I'm just going to call it y. Okay, with that being said, I can find an equation for this section. Okay, you know that this section that I have over here is going to be 5 minus y. Are we okay with that? Because the entire thing from here to here is 5. Okay, so I know that that one has a cap. Okay, with this being said, you know that this is forming a right triangle. Therefore, this is going to be your hypotenuse. With that being said, you have the legs, the value or the equation of the legs. Therefore, your hypotenuse here is going to be 1 squared plus, and then you have 5 minus y squared, and then you have that this equation is going to be all of it inside the square root. Okay? So you have this equation inside the square root. Now, what are we going to do? This equation that we have over here are distances. Okay? This is the distance. But the question here is, and they are telling you that they want to minimize the time of this guy. Okay? So the minimum amount of time. So you need to remember something. Time is going to be equal to the distance between a rate. Okay? Do you have the rate? I actually do have two rates. Okay? Those two rates. Therefore, my equation here, it's going to be based on y's, because all this situation that I set up over here, it's based on y's. I mean, you can set it up with x's, but here I chose y. So y is going to be equal, and then you have the swimming piece and the walking piece. Let's start with the walking piece. You know that the distance of the walking is going to be y, and the rate is going to be 6. Similarly, you have that the swimming part is going to be 1 plus, and then you have 5 minus y, everything square, and then everything inside the square root. Okay, and this is going to be divided by the rate of the swimming, which is 3. Okay, so at this point, what are we going to do? At this point, what you can do is we know that we are going to take the derivative of this equation to minimize it. Okay, and then we're going to equalize it to 0, so we're going to find the critical numbers, and then that's pretty much it. Okay, well, we test the values and we see what's the min. Okay, so here I'm going to simplify a little bit my equation. Okay, so what I'm going to do here, you know that this is going to be 1 plus, and you know that it's 25 minus 10y plus y squared. Okay, so you have this equation here. Let me just do it like this, otherwise it's going to look like a mess. Then you recognize that these two are like terms. So what I have here is going to be y divided by 6 plus, and you have the square root of 26 minus 10y plus y squared, and everything divided by 3. So I have this situation, okay, which is not very user-friendly still, but that's what I'm going to take the derivative of. Okay, so we take the derivative of that situation, so I have that t prime of y is going to be equal, this is a 1 over 6, plus, and then the derivative of this equation is going to be the 1/3 times a 1/2, because you know that this is going to be to the 1/2, times you have that it's going to be 26 minus 10y plus y squared to the power of negative 1/2 times the derivative of the inside, which you know that it's negative 10 plus 2y. Okay, so you have that that's your derivative. Okay, you can recognize that both terms have 1 over 6 as common factor, so I'm going to take it out. Let's see if that helps me a little bit at least, and I'm going to rearrange this equation. So you know that this is negative 10 plus 2y, everything divided by 26 minus 10y plus y squared to the power of 1/2. Okay, please note that this is a 1 over 6, and I'll pull it out here. Okay, and this 1 over 6 is this one that you see here. Okay, so you have this equation. This is as simplified as we can. Remember, here I use properties of exponents. I took this negative 1/2 to the bottom. So I'm going to equalize this to 0. When I equalize this to 0, I pass the 6 multiplying the 0, so that one disappears. Then I need to move this one to the other side. So what you have to solve for y, you have that it's going to be 1 is equal 2, and you have that since it's going to be negative, I'm going to change the sign, 10 minus 2y divided by 26 minus 10y plus y squared, okay, to the 1/2. Okay, so at this point you are like, I don't know what I'm going to do. Well, this is kind of like a trip to algebra 2. Okay, over here you need to pass this multiplying to the other side, and do you agree that you have something like this? So what are you going to do to solve this equation? Well, my thinking tells me, you know what, I'm going to square both sides. Okay, and your thinking is correct. Okay, so with that one, you have that it's going to be 26 minus 10y plus y squared is going to be equal to, you have that it's going to be 100 minus, and that's going to be 40y plus 4y squared. Okay, so you have this equation which looks pretty similar to an algebra 2 problem. You know that I need to pass the like terms to the same side. This looks like a quadratic, so I'm going to pass everything to this side. So I have that 0 is going to be equal to 3y squared. Okay, so this I already accounted for. Then I pass this one to the other side, having negative 30y, and then you have that it's going to be plus 74. Okay, so at this point, what are you going to do? This is not factorable because you know that 74 is not divisible by 3. Okay, then your only choice here is to use the quadratic formula. Okay, when we use the quadratic formula, you have that y is going to be equal to 30 plus minus the square root of 30 squared minus 4 times 3 times 74, and all of this is going to be divided by 2 times 3. Okay, so at this point you are like, oh my goodness, this is a monstrosity. Well, kind of. Okay, so when we try to simplify this, what you have is that this is going to be 15 plus minus, and it's going to be the square root of 3 divided by 3. Okay, at this point you are like, oh my goodness, how in the world I'm going to know what to do with this one? Well, here in the situation that we have, let's go back to our graph. You know that your y, okay, here, it's limited to be 5, and the minimum it can be 0. Okay, so why is that? Because you know that the distance between the guy and basically in front of the camp is 5. Okay, so we have this closed interval. Okay, and you have that pretty much 15 plus root 3 divided by 3, it's above 5, because 15 divided by 3 is 5, plus root 3 divided by 3, that's over my interval. Okay, so you know that the only solution that I have here, my only critical number that works for this problem, is going to be this one. Okay, so at that point you are going to do your EBT, your table. Okay, so what we're going to do here, I'm going to do my little table here. Okay, you know that I'm going to have here my y and my t of y. Okay, so what are you going to do here? Well, here I'm going to put my extremes. As I mentioned a second ago, this is 0, this is 5, and then here you are going to put the 15 minus root 3 divided by 3. What are we going to do with these values? Well, you are going to plug them into your equation here. When I plug the 0, look at the 0. This is 0. This is 0, but this is going to be a 25 plus 1. So this is root 26 divided by 3. So that's just the 0, right? Which is horrible. If you want to approximate that, by the way, that's going to be roughly 1.699, which is an ugly number. So at this point, what I'm going to do, I'm going to plug this one into my equation over there in the calculator using my calculator. Okay, so if I plug that one in my equation, I know that it's going to be, what was it, 15 minus, and then you have that it was, actually we can compute the 15. First I'm going to do 15 minus, and then you have root 3. And then I'm going to divide everything by 3 so I can have the decimal. Okay, so we have the decimal there. So I'm just going to copy the decimal to the equation, okay? So you have that equation divided by 6 plus parentheses, and I'm going to put the square root, and we have that it was 1 plus parentheses, and then you have that it was 5 minus, and I'm going to put another parenthesis so I can copy that situation, and then you have that that one was square. Okay, and then we have that that's going to be divided by 3. Okay, so we have that it's 1 point, I don't know if you can see it there, it's 1.122. Okay, so I'm going to repeat the same process for the 5. Okay, and what I got when I plug the 5 is 1.167. Okay, so you compare the values here. Okay, and the smallest that you have here is this one, therefore this is going to be your minimum. Okay, so again in this problem we have that by extreme value theorem. Okay, we have that to minimize his amount of time, the man should walk, how much time should he walk? We know that y, what's the y? This one, okay? 15 minus root 3 divided by 3 miles, okay? Before swimming across the river. Swimming, okay? The river, and that's pretty much it. So let me show you here the conclusion, so you have it. You could also put here the 4.423 that I found in the calculator before. Okay, either or would be the same as long as you have your units. That should be fine. Okay, and that's it for optimization day 1. I hope that you find this video helpful. Bye.